So please welcome our next speaker from the Research Center for Theoretical Physics, Dr. Alfilgen Sebandal, one of our young and promising mathematicians, here to talk about her work on the adjacency matrix perspective of talented monoids.
Thank you, Dom. I hope it's everyone can hear clearly.
The mic is on.
Yeah, I think that my mic up. Please, can someone please verify if you can hear me?
Yeah, you are audible.
Okay, thank you so much, Deepak. Okay, so now I will just assume that some of you might not be here earlier, so it means that I'll be defining some terms again. But this time, of course, it's a research talk, so it's not as detailed as earlier, because we had this introductory lecture on graph and talented monoids earlier. So my talk is on adjacency matrix perspective of talented monoids. If you would be interested, especially in an adjacency matrix perspective, we have here 5 publications on talented monoids and Leavitt path algebra. In particular, for adjacency matrix, that is this second paper here. Okay. So if you have a directed graph, then you can associate many things. Earlier today, we have seen 2 monoids. First one is the talented monoid and the graph monoid. Now we are looking at the so-called Leavitt path algebra. I forgot if I defined it formally here, but let's see. Let's surprise. I will surprise myself as well if I formally defined Leavitt path algebra. And there's a connection between Leavitt path algebra and talented monoids. And the question would be, how are we gonna connect these 2 things? Let's say, are there things that are true here? Let's say a property P, then probably there's another property P prime that would say that it's true here, and this P prime should be related to the property P on Leavitt path algebra. In particular, Rusbe Hazrat, who is my supervisor from Western Sydney University, Australia, in 2013 conjectured that you can actually classify the talented monoids in terms of classification on the Leavitt path algebra side. So when we say we are classifying things, let's say I have fruits, then I will classify my fruits based on type of fruit. Then I will group all of the bananas together, all of the let's say apples together, or let's say I'm grouping by color, which means that I'm grouping fruits which are color red, which are color pink. Is there a pink a pink a fruit? Anyways, so the idea is that there's something that is telling us how we are grouping things. In particular, in the talented monoid, there's what we call Z isomorphism of talented monoids. Earlier today, we have learned that the talented monoid is actually a Z monoid, which means there is an action on the group of integers on the talented monoid, and it's just your good old homomorphism of groups. Just imagine on that, and this homomorphism is some sort of respecting your action, and you make it bijective, and you have an isomorphism. On the Leavitt path algebra side, we are not looking at, or Rusbe did not look directly at Leavitt path algebras, but rather on categories. In this case, categories of graded modules over the Leavitt path algebra. And since these are graded modules, the equivalents in the categorically are graded equivalents. We are not gonna dig deeper into these notions, but rather it's just an overview of how the classification is going on. And good for us trying to answer this conjecture, Rusbe, in the same time when he conjectured this result that we see here, or this thing, he also said that, okay, there are a certain types of graphs satisfying graded classification conjecture, and it's the polycephaly graphs. What's a polycephaly graph? Okay, I think I have a different, I can remember a different slide next, but anyways, probably it's gonna be in the next ones. But in this presentation, my focus is on another world, not on the Leavitt path algebra directly, but on the adjacency matrix. So given a directed graph, you can also associate an adjacency matrix. As a matter of fact, they are actually equivalent things. If you have a matrix which has entries, non-negative integers, then you can directly say that it's a directed graph, which I will define later, hopefully, if I have the correct presentation. But just to see when this Leavitt path algebra and talented monoid came into existence, the Leavitt path algebra was introduced around 2005, 6, 7 by Abrams and Pino, their paper, and another paper by Ara, Moreno, and Pardo. As you see, there are two groups of people introducing Leavitt path algebra. The reason for this is because at this time, they didn't know of the existence of the others' work. They were simultaneously but independently working on Leavitt path algebra, which is pretty amazing for me. On the talented monoid, on the other hand, it was introduced by Hazrat in 2013, but at this point, it was not yet called the talented monoid. It is also not of the form where we see in this presentation. Actually, it is a monoid that is related with the Leavitt path algebra at this point. In 2020, he and Lee, Lee, actually coined the term talented monoid, and the form of this monoid, which we see here, was already formulated at this time. And if I have more time, I will be adding some additional results on Lee bracket. So my title would be, if I have a more time, of course, it's gonna be adjacency matrix and Lee bracket, perspective of talented monoids. Let's see. Okay, I know now what happened. All right. So what's a polycephaly graph? If we remember, the graded classification conjecture is true for polycephaly graphs. If you know polycephalic creatures, it's actually creatures having one body and multiple heads. Similarly, it looks like this example here, where I have one body given by your paths probably, or maybe this is the neck, and you have multiple heads. What actually a polycephaly graph is a graph where every vertex or every path in your directed graph is either heading towards a cycle, an end petal loop, or a sink. A sink is a vertex that is not emitting anything. So that's essentially the definition of a polycephaly graph. And I've said earlier, how do we define a directed graph? We have here a visualization of, if I would be a, let's say, high school student, if you tell me, if I hear the word directed graph, this is essentially what I imagine right away. Set of vertices and set of edges connecting your vertices. But you can also define it in a more, let's say, algebraic way or mathematical way, where I just say I have four things. Two are sets and two are mappings. Two sets, e to the 0, e to the 1. For the meantime, let's just imagine this is any set you can imagine. And two mappings, S and R. S actually stands for source and R stands for range. So if I have a mapping S and R from the set e to the 1 to the set e to the 0, what I'm actually having is a mapping which sends every edge with source, with the mapping source to this, well, what is it? Head of head of the arrow. And this is tail, right? And this is the tail, the range. But you can think of e to the 0 and e to the 1 as any sets that you can think. But visually, or in this way, this is what we get. Another way is through adjacency matrix. So let's see what it is. If I have this graph E here, what an adjacency matrix is basically a matrix representation of your directed graph. If I have vertices U1, U2, and U3, I will just lay these vertices horizontally and vertically here and here. So let's see. Let's look at the entry 1, 2. So this guy. So this is 2 because in your graph E, there are 2 edges pointing from U1 to U2. And there is 1 in entry U3 or 3, 3 because there is 1 edge coming from U3 going to U3. And I think I forgot this U3. Yes. This should be 3, 2. So this should be 1. All right. And of course, the others are 0. And one observation is that if we have a 0 row, what does it mean? 0 row. It means that this row corresponding to the vertex U2 or the yeah, is not emitting anything. It's a sink. On the other hand, if there is a 0 column, then this vertex corresponding to this column is what? There's no edge going to that vertex. So U1, there are no edge going to that vertex. Okay, it's a source by definition. A source is a vertex where there are no edges going to that vertex. Now, a small computation. If you have some time, try to compute adj e squared. I think it's pretty easy, but I'm so bad with matrices and matrix multiplication. But let's see. I will guess that I will just guess at this point. So I am not computing anything. I am not computing in a matrix way, matrix multiplication. But actually, and you can probably guess by yourself, I will just say that this is 0, this is 0, this is 0, this is 0, 0, 0. I will explain why later. This is 0, this is 1, and this is 1. Okay. I hope I'm correct. Maybe I'm wrong because there's 2, then there's no more 2. Anyways, what I did actually, and you can correct my computation if I think there's a mistake, but what happened actually here is that the entries in this adjacency matrix raised to 2 are actually the number of paths of length 2 from this vertex to whatever vertex you have here. For example, let's see as U3, U2. So this entry. How many paths of length 2 have source U3 and range U2? 0. This is 1, 1, 2. So that's why I put 1, because there is one path of length 2 with source U3 and range U2.
Sorry, I was looking at the prior matrix. You corrected that already to have 1 at the bottom.
Oh, yeah, sorry.
Yeah. Okay, sorry. That's why.
Okay, I'm so sorry. This should have 1 here.
Yeah, there we go.
Okay. Sorry for that. Thank you, Dom. And similarly for U3, you can multiply this guy to itself again, or you can just ask yourself, how many paths of length 2 has source U3 and range U3, which is just 1. So I have 1. So it's a pretty handy way. If you don't like multiplying matrices like I do, I don't like it. And you just try to say, okay, I will make my directed graph out of an adjacency matrix, or sorry, a matrix having non-negative integer entries, and then I ask myself how many paths. Maybe that's more lengthy way, but it's another way. Anyways, okay. So again, we are gonna connect that to the adjacency matrix. I think I had mixed up with my slides. Now, for those who have seen me talk before, let's welcome the animals again. Okay. Before I introduce the graph and talented monoids, a motivation for that is this story of the so-called mad veterinarian puzzle. So there is mad, but also at the same time crazy and genius mathematician, or he's a veterinarian, and he is working with three animals: beaver, cat, and ant. And he coined, or he what do you call that? Invented a machine, and this machine does magical things with your animals. If he puts one beaver inside of your machine, then it produces the animals beaver, cat, and ant. So it means that this machine does not just change your animal, it also produces more animals. The question if, and okay, and let's say that this is the other transformations that we get using the machine, this one that we see here, which means that if I put one ant, I get one beaver, and vice versa. If I put one beaver, I get one ant. And the question would be, if I have one ant and I use the machine again and again and again and again, and having different combinations of animals being put inside your machine, is there a way for me to get two cats actually? Now this simple process tells me that yes, I just put inside one ant, and I get one beaver. Then from one beaver I get these three animals, and I will just keep my cat and then put these two guys inside the machine, and I will get one cat. Is there a question? There's no question. All right. Now, of course, you can do that, but the thing is that it's gonna be tedious task. And what would happen is the mad veterinarian will take out this heavy machine and it's gonna put the heavy animals, and it's just tedious and it's tiring. So let's try to make this more efficient by putting it in a mathematical way. Let's say that this transformation is actually viewed as a directed edge coming from the animal going to the animal it has produced. So for example, this transformation here would mean that there is a edge source cat and range ant. Now, it turns out that this entire scheme here can be viewed as this entire graph. So there's a loop on the beaver because if I put beaver inside, then I get also the beaver. Abrams and Sklar actually utilized the so-called graph monoid in answering the mad veterinarian puzzle. Oh, it's not. All right. What is a graph monoid? You just take all of your vertices. So your graph monoid, I will denote that by M sub E. You just take all of your vertices and generate your monoid, and you subject that to some relations, which the relations would be V would be equal to all of its ranges, and these edges are having source B. Okay, so that is why if we look at this graph here, B is equal to A plus B plus C because B is emitting A It's emitting B and it's emitting C. So that is why we have these equations here, which looks pretty familiar because it looks just like your animals. I mean, these are your animals essentially. So in a more detailed way, this is your graph monoid ME. And you do that for non-sinks, which means that there is a edge emitted from your vertex. Therefore, the calculation that we already did earlier is actually a calculation on your graph monoid. And A would be equal to 2C. To make it just a little more complicated than it looks, because it looks so simple, so let's make it a little complicated. If we look at Leavitt path algebras, actually, if you collect all of the finitely generated projective modules and you take the binary operation being direct sum, then you will get a monoid, and that monoid would be actually equal to your graph monoid. It's just some motivation on the relationship of graph monoid and Leavitt path algebras. Okay. A variation of this puzzle would be putting some ages in your animals. Let's say I put a beaver of age n. And what the machine does is it increases the age of your animals by 1 unit. The question would be, okay, I have a 2-year-old ant, and I know that I can produce 2 cats. But how old are these cats then? What we would do, for example, let's just work on the graph monoid sense for the meantime, but later on we will define it another monoid. Let's say I have A, and let's say that's 2 years old because I have an ant of 2. So that's gonna be B of 3 because A goes to B, and I'm just gonna increase 1 to this index 2, which is now gonna give me 3. I do this again. B is emitting A, B itself, and C. And I again increase 1 on the index. So 3 becomes 4, 4, 4. And I just keep this guys here. And I know that cat or C of 3 would be equal to this. So since it's equality, I can do it both ways. So this guy would be equal to this one. Therefore, although this doesn't make sense because it seems like the cat or the animals lose age. But the idea is that in this case, if I have an ant of 2 years old, I will get 1 cat and 2 cats, 1 of age 3 and 1 of age 4. But what we did actually is a computation on the so-called talented monoids, what it is. Earlier, the graph monoid is a monoid generated by your set of vertices subject to some relations. Now, on the other hand, a talented monoid would be, again, another set, a generating set. This time, I have a set containing V partnered with a integer I. And I subject that to some relations being V of I equal to all of the ranges, summing them up, but now adding 1 on the index. So it means if I have U of I, this talented monoid relation tells me that it's going to be equal to X of I plus 1 plus Y of I plus 1 plus Z of I plus 1. So very, very simple. But again, let's make it a little complicated in comparison to the graph monoid earlier. Similarly, the talented monoid is also related to the Leavitt path algebra. In this case, if we collect all of the graded finitely generated projective modules over your Leavitt path algebra, so the only difference is that I'm looking at graded modules at this point. Earlier, it's just any modules. And similarly, your binary operation would be direct sum, and take that as a monoid if you take all of them. And it was shown in 2018 that monoid is actually your talented monoid. But the question would be, if I have a graph monoid and I have a talented monoid, probably they are just the same. Maybe it's not worth the time putting ages on your animals or some indexing. But if we look at this example, E and F, and if we try to compute its graph monoid and its talented monoid, its graph monoid are actually isomorphic, which means in your good old mathematician language, they're essentially the same. But your talented monoids are not isomorphic. What this tells us is that your talented monoid is more successful in classifying your graphs, which probably would tell us also that it's more successful in classifying your Leavitt path algebras, for example. Okay, now let's try to see how the adjacency matrix comes into the game. That is through the so-called hereditary, or at least in the first few results of my presentation, through hereditary saturated sets. The Leavitt path algebra, if we take all of the graded ideals over your Leavitt path algebra, actually your hereditary saturated sets are generating such ideals. On the other hand, if we take all of your Z-order ideals, such Z-order ideals in your talented monoid are also generated by some hereditary saturated sets. So I'm not defining these terms yet. And this happened 2017 and 2018. And in 2022, just last year, me and Dr. Bok have formulated similar point of view, but in the adjacency matrix point of view at this time. And we called it hereditary saturated submatrix. So it's, I think I have seen hereditary matrix before, but this is different to that matrix, and we will define it later. But what first, hereditary and a saturated set of vertices? If I have a set of vertices H, and if U is inside H, if this guy is inside H, and I say that H is a hereditary set, then I will be forced that these guys, all of the ranges it's emitting are also inside H. Similarly, not similarly, on the other hand, it's saturated if all of the ranges are inside, then the source should also be inside. Now, Z-order ideals. It's generating your so-called Z-order ideal. But what first is a Z-order ideal? The set of integers, that's why it's called Z-order ideal. Actually, this is why there's Z is coming into the game, because the set of integers is acting on the talented monoid via monoid automorphism, or via shifting of indices rather. So if I denote my action of n on an element b of I into this form, then I would say that the action would just be this shifting of indices. I'm just increasing the index by n. And this, you just extend this in a natural linear way. And because of this, you have an action on the set of integers on the talented monoid, which will tell us that your talented monoid is a Z monoid. In general, if you have a group gamma, which is acting linearly on a monoid M, then your monoid M would be called a gamma monoid. A Z-order ideal now would be a subset of your talented monoid, which satisfies this equivalence statement here. What this just means is that I have a submonoid, which means it's closed under your operation, plus it's also closed, or it's closed on the action, which means every action is actually giving you a different element in your Z-order ideal, and you do it in an equivalent way, which means that if this A and B are inside A, then I have this, but we don't stop there. We also do it another way. If I have this summation, then A and B should also be inside here. Z-order ideal I. Okay. Now, what is a hereditary saturated matrix? And as what you have already, I have told you, Such matrices are determined by your hereditary saturated set of vertices. What that is just a submatrix of your adjacency matrix where you can permute your elements or your set of vertices in a way where we get a block. So that's called just this block as an adj H, because this is gonna be a block with having which is an adjacency matrix of a subgraph, and where its corresponding entries on the right would be 0, and A and B, these are subblocks, where if all of the entries on a specific row on B is 0, then that row on A should also be in 0. So you might already know what's happening here. On this side, this is giving us hereditariness, because it just tells us that all of the connections are preserved inside, because connections outside are non-existing because you have a 0 entry here. On the other hand, if this is 0, which means that it's not emitting outside of H, then this should also be 0 here, which means there's no connection with it. All right. So this is your hereditary saturated matrix. Let's try to connect that graphically and talented monoid point of view and adjacency matrix point of view. Let's say I have a graph E here. Let's collect some hereditary saturated subsets of this graph. H3, the entire thing, of course, is a hereditary saturated set, of course. And in the set-wise notation, I have e to the 0, I have the talented monoid, if I have everything, and your adjacency matrix. Now, I will go one step lower. Let's say I will collect all of these vertices here. You can check that this set of vertices is a set of hereditary saturated set. It's a hereditary saturated subset. Now, in terms of vertices, I get this, of course, what I've said earlier. In terms of the talented monoid point of view, I get a Z-order ideal generated by that set. And in the adjacency matrix, I get this adjacency matrix, which will be your submatrix. And that will be a hereditary saturated submatrix. Let's now again go down one more. Similarly, this collection of vertices is hereditary unsaturated, which means I will add in my chain here. Similarly, since such sets are generating your Z-order ideals, I again have this inclusion here. And now looking at, so this should be 2. This was 2 earlier. I hope this entire thing is 2 earlier. And this is gonna be your sub-block, which comes from your adjacency matrix of H1. So what we get? We see that we have a sequence of hereditary saturated sets here, which turned out to be a sequence of Z-order ideals and some sort of sequence in your adjacency matrix. As a matter of fact, that's what I've said earlier. Have a sequence, and a sequence. But okay, probably one could ask, maybe this sequence might not be unique. Maybe I can reform my matrix in such a way that I get a different sequence of. That's actually possible, but maybe also not. Maybe it's possible, but maybe we can hold on the length rather than the actual sets. What is the length? In this case, I have n what do you call this? Sets. Here I have n Z-order ideals, and here I have n submatrices. So what is n? Maybe we can instead look at the sets itself, because maybe they're not unique. Maybe n is unique. Let's see. In the sense of groups, we have the so-called composition series. which is just a sequence or a chain of subgroups. And if the quotients of these groups are actually simple, then you have a composition series. In groups, the length of such chain is actually unique, which means if I have a different sequence, but actually is still a composition series, whatever that is, its length is unique. Similarly, in the talented monoid, we have the so-called Z composition series. So, question, if this N here is unique, and we know that this correspondence is existing, then this N is unique, and this N here is also unique, which means I can say I have some sort of length N, some sort of length N. That's a question. Well, we have a version of the Jordan-Hilder theorem for this is the theorem that tells you that your length is unique. We have that version on your gamma monoids, and that is true for some sort of not all gamma monoids, but refinement gamma monoids. It just means that what is refinement? I will not define it, but it just means that every summation in your monoid is actually refined in some way. Okay, in a refinement gamma monoid, such lengths is unique. And good for us, the talented monoid is a refinement monoid, gamma monoid, Z monoid. So it means that this length, which is N, will tell us that actually I will also have a sequence of submatrices exactly of length N as well. Maybe not length N, but N plus 1. But the sub blocks would be N. Okay, maybe it's not. There you go. So where else can we use the notion of adjacency matrix? We have seen that in the talented monoid, the adjacency matrix is useful in determining the length of your Z order ideals. At the same time, adjacency matrix is very handy in trying to compute the vertex, relations in your talented monoid. What this very I don't like complicated viewing equations, but what essentially this theorem or proposition rather is telling us is that, for example, V1 of 0 would be just a computation in your adjacency matrix in this way. So you just compute this, and you will get an entry of V of 1 of whatever the entry in the corresponding computation would be. Okay, and all right, okay, that's the idea of this proposition. Next, where else can we use that? We can also use adjacency matrix in computing the number of linearly independent elements of your Leavitt path algebra of length k. So again, I will not explain what's happening here, but the idea is just how useful the adjacency matrix is. But where else can we use the notion of adjacency matrix? Okay. Now, before we go further, I will define the so-called Gelfand-Kirillov dimension. But again, I don't like these things here. Personally, because I'm an algebraist, I don't like seeing limits. I'm so sorry for those who are in analysis. But basically, what Gelfand-Kirillov dimension is taking the limit of some sequence. And what this sequence is actually determined by dimension of a sequence of subspaces. And these subspaces are determined by your lengths. Okay, let's just say like that. And you take this limit, and if you try to compute the Gelfand-Kirillov dimension of this, or of the Leavitt path algebra of this graph here, you get 5. Okay, I don't know how to compute because again, I'm not good. I'm really bad at these things. So maybe there is a different way of computing the Gelfand-Kirchhoff dimension without looking at subspaces and without looking at limits. Good for us, there is, and that's a result by Alamedi, Al-Sulami, Hain, and Zelmanov. They say that if the graph contains cycles which are not joint in any way, which means that they are not sharing any common vertex, then the Gelfand-Kirchhoff dimension is finite. In this case, I will just look at the length of some chains of cycles, and I take the maximum length, I call that D1, and I also take the length of chain of cycles now with an exit. Exit means that I have a cycle and there's an edge coming out of that cycle, and I call that D2 being the maximal, and the Gelfand-Kirchhoff dimension would be this very, very, very easy computation here. Therefore, here, D1, what is the maximum length of chain of cycles? I have a chain of cycles is just, what is it? I did not define. It's cycles that are connected by a path and forming a chain, some sort of chain. So this is a chain of cycles of length 3 because I have 1, 2, 3. So, which also corresponds to the maximum length. Now, D2, we should consider chain of cycles with an exit. This doesn't have an exit, this cycle here, but this cycle has an exit, which is this one. So, and this is also a cycle with an exit, but I'm looking at the maximum. So I'm gonna take this one, which has length 2. Therefore, simple computation would tell me that GK dimension is equal to 5. But how about graphs which are not actually having disjoint cycles? We know by this theorem here, this lovely theorem, that I have an infinite Gelfand-Kirchhoff dimension. Probably there is another notion that could cater such graphs because we already get infinite here. Maybe there's a different notion. And to cater such graphs, there we have defined the so-called algebraic entropy of a filtered algebra. If you have a filtration, it just looks like there's a sequence of some sub-algebras in your graph, in your algebra, and it just satisfying some things. That's a filtration. And you take a look at those sub-algebras and say that, okay, if A is finite dimensional, microphone.
Yeah, I think you're muted.
Accidentally muted.
Oh, really? Okay, okay. Huh? Hello?
That's how this one. Oh, no, it's not.
Can you hear me?
She's not muted.
Yeah, you're fine.
This is my mic.
Maybe
Yes, Alfie, you're audible.
Speak a little louder.
Sorry. Can you hear me?
Yes, you're audible.
Okay. Thank you. Sorry if you are talking to us because I put the volume down earlier, but now I can put it back again. Sorry. Thank you. No worries. No problem. Okay. So again, this algebraic entropy, the hope would be we are gonna cater graphs having joint non-disjoint cycles, which we are joint cycles. So this cycle is joint with this cycle. Okay, if we look at this definition, it looks like your Gelfand-Kirchhoff dimension, but it's just tweaked little bit. That's the difference there. But I will not go further there. Okay, but it's what I just want to share is that the algebraic entropy of this guy is actually logarithm of 2. And in comparison to the Gelfand-Kirchhoff dimension, for example, if we look at this, if we have a graph with disjoint cycles, the Gelfand-Kirchhoff dimension would be finite, but its entropy would be 0. On the other hand, if I have a graph with non-disjoint cycles, they are joint, the Gelfand-Kirchhoff dimension would be infinite, and the entropy would be some finite number. So it just means that we are able to cater them. But in the sense of adjacency matrix, how can we utilize adjacency matrix in these two notions here? But it would be also interesting to know, actually, that if I have isomorphic talented monoids, your Gelfand-Kirchhoff dimensions are equal. So the natural question is, if I have isomorphic talented monoids, would their algebraic entropy would also be equal? This is still an open question. So if you are interested, you can try in solving this. So how do we use adjacency matrix? Adjacency matrix actually allows us to compute your algebraic entropy in this very lengthy way. And just believe me when I say that that's the algebraic entropy, which is pretty handy. Okay, I don't think I have enough time anymore, so thank you so much, and I will not go to the brackets anymore. Thank you so much. If you have any questions.
And thank you for our speaker.
Thank you.
Talk. If you have any questions, please do so in the chat. We have some questions. Let's do the chat first. If you have any questions. Oh, am I too weakly speaking? If you have any questions, please just chat or turn on your mics. Thank you. So may I ask my question? Could you go back to the part where you're talking about the Jordan-Hilbert theorem? Wow, it spins.
The Jordan-Hilbert theorem.
Yeah. Oh, sorry. Should I pronounce it German?
I'm actually not sure how to pronounce it correctly, but one is Hilder.
Yeah.
Hilder.
One of those. I don't know. I don't see. Oh,
where is it again? Yeah, I think no.
Because you're essentially you're applying this Jordan-Holder theorem for hereditary ideals, right? And then applying that to the monoid for the Jordan-Holder theorem.
Yes.
So in this case, since we know the Galois correspondence between these ideals and the monoid, so how would we assure that we will get simple quotients on the adjacency matrix? So
there's also
so we have HI and then HI plus 1. For this to be a simple quotient, I would assume that I would take the smallest hereditary subset corresponding to that contains HI, right? Or something like that.
Smallest hereditary saturated submatrix.
Yeah.
In the matrix.
Yeah. For the matrix. But for the set, I get the smallest one containing HI that is also saturated with hereditary.
Yes.
Okay.
Yes, sir.
So that's good.
I did not define earlier. There's also a notion of some sort of composition series in your matrix. I did not define it earlier.
In general, or just
no,
the correspondence with you just reduce the definition to the correspondence in the monoid?
Well, the correspondences are motivation in the definition. Yeah.
And then so here sorry, not here, but in your definition of the filtration, I just wanted to see how you define your
maybe filtration. I did not define. Actually, I did not define filtration.
No, just how you define what did you take for the filter? What was the WI here?
Okay, let me remind myself. It has been some time. So WI, let's say the linear span, well, W0, take the linear span of paths of length 0, which corresponds to the set of vertices. W1, you take W of 0 and then you add that to the linear span of those of length 1. That includes, length 1 and negative 1. Because in your ghost edges are of length negative 1. And you do that for every k. Yeah. By the way, for those, because I did not define it as this E1 star are actually ghost edges. If you think of an edge and then you flip its orientation, meaning the source becomes range and the range becomes source, that is the so-called ghost edges. And technically that has degree -1. So that's why we are saying here that you take those edges or those elements with degree positive or -1.
I also have a question. For the font parallel dimension, you have a formula there where just you look at the graph and then you find the number dimension. But for algebraic entropy, did you also have that one? Or
Yes.
not yet?
Yes.
Wow.
Okay.
Did you put it there?
No, I did not put it.
That's why I didn't say.
Okay. Actually, in the case of algebraic entropy, what we have shown that I did not put it here is that you take the spectral radius of your adjacency matrix. So in this case, you don't look at the graph similar to the Galfan-Field of dimension, simple looking at the graph. In the algebraic entropy point, you take the spectral radius. You look at that.
But that's for the adjacency matrix.
Yeah, but not for the
But
graphical.
Like for example, the other one for the Galfan-Field dimension, you just look at directly the graph, but not for the algebra.
That would be nice, but
Maybe. I don't
maybe
know.
it's
Something
possible.
to look at.
Yes.
So look at, so that you just look at the
graph.
graph and then you can get the
Question, sir?
So here in the standard filtration is just from the grading, right? So you just take yeah, essentially, yeah, that's it. Right?
Yes, you are right.
Except of course it's now not direct because you're taking the ones that are less than 2, for example, you get 0, 1, and 2, 3, 0, 2.
Yeah.
And then, one last thing. When you were talking about the conditions in the algebraic part, right? A couple of slides after this, for when you're looking at this dimension using the entries of the matrix. What norm are you using?
Oh no, it's not a norm. I'm so
Okay,
sorry.
sorry.
We have
the formula.
Yeah.
this one.
It looks like a norm.
It looks
right?
like a norm, but it's not the norm. It's not a norm at all.
Okay, sorry.
No worries. I also did not define, so it's my fault. This is some sort of adding of entries in a particular row or column.
Adding certain entries.
Yeah.
Okay. Oh.
So that's why you see C here, superscript C, because this tells me that okay, what maybe I should.
So I was like surprised. Wow, there's an there's an AJ norm for that.
No. Okay, I will explain what this is. So A to the S. Yeah, it looks like a norm. A to the S is your usual S exponent of your matrix.
Yeah.
This C here will correspond to column. This by column, I'm just saying that I take the jth, if I remember correctly, I hope so, the jth column, and then I add all of those entries in the jth column.
Okay.
So that's the
notation.
Okay, so it's the L1 norm on the jth column.
Oh yeah, I have.
okay,
Yeah.
Sure. What's the S here?
The S power of the
Yeah, it's just there.
Matrix.
When you have S plus T is equal to K. L? L?
Where?
S plus L is equal to K.
S plus T.
Where?
S plus T. T is here.
Yeah, there. So
it matches the filtration.
Yeah. So
Yes, definitely.
is adding columns no. Right. So that's why.
Yeah.
Confusing to see that.
Yeah, I'm so sorry, especially to those who are in the analysis. they look at this as norm. I'm so sorry.
Adding of the entries, not just in a single column, that is a norm.
For everything. Yeah.
So that's why. So maybe I don't know.
We have question, guys, for those who are in the Zoom.
What will we be sending them for lunch?
If there are no questions, thank you everyone for, there will be no certificates anymore. Thank you everyone for coming, and we really, really, really appreciate your attendance. Hope to see you this afternoon for Dom's talk. Yeah, for 3 p.m. I might update the Facebook announcement because we just recently got confirmation as what do you call that we are allowed to share the link. So if you are interested, you can find it in the RCTP Facebook page. Thank you so much and have a pleasant afternoon.
Thank you. Have a nice lunch or whatever time zone you're in.
Thank you. Bye bye.
And you'll have our organization.